Hey everyone, ready to dive into something pretty mind-bending?
Always.
Okay, great. So today we're looking at conservation laws in physics, symmetry, and how they might apply to information itself.
Sounds intriguing.
It is, it is. We're going off of this chapter from a book I read recently, and it really got me thinking. Yeah, like, could there be a hidden conservation law governing information, much like the ones we see with energy or momentum, you know?
That's a fascinating question. We tend to think of information as this kind of abstract thing.
Right.
But what if it actually follows the same fundamental laws as, like, the physical world around us?
Exactly. And this chapter starts with something I think we're all pretty familiar with, the first law of thermodynamics.
Right, right.
You know, the whole idea that energy cannot be created or destroyed, only transformed.
Yeah.
And they use that as a starting point to explore some much deeper concepts.
The first law is a good place to start, I think. Imagine, just picture this. You've got a super hot cup of coffee, and you move it, from your kitchen to your desk.
Okay.
The location changes, obviously, but the system itself, the cup, the coffee, all the energy in it, that stays essentially the same.
Right. It undergoes a spatial transformation, but the total energy is conserved. But what if we took that idea and applied it to something a little more dramatic?
Like what?
Like, say, a high-speed car crash.
Ooh, now we're talking. Okay, so the cars themselves obviously transform dramatically.
Right. Cool.
But the total energy involved, that remains constant. It's converted into the kinetic energy of the impact, the sound of the crash, all the heat that's generated, the light that's emitted. It's this crazy, wild dance of energy-changing forms. But it never actually disappears.
I'm with you so far. Energy can't be created or destroyed, only transformed. But so where does symmetry fit into all this?
Okay, well, this is where things get really interesting. There's this amazing principle called Noether's theorem.
Okay.
Named after Emmy Noether, this brilliant, brilliant mathematician. Even Einstein was impressed by her work. He saw her as a true genius.
Wow.
And what Noether's theorem shows us is that for every single conservation law in physics, there's a corresponding symmetry.
So it's not just about, like, things looking symmetrical, right? Like a perfectly mirrored butterfly or something.
Right.
We're talking about symmetry in a more kind of abstract, physics-y sense.
Exactly. Think of it like this. If you perform the same action in different parts of space or at different points in time, and the result is the same each time, then you have spatial or temporal symmetry.
So, like, if I throw a ball here, it'll behave pretty much the same as if I threw it across town. I mean, give or take some minor gravitational differences, of course.
That is a perfect example. You just demonstrated spatial symmetry in action, and that's directly linked to the conservation of momentum.
Okay.
And if you threw that ball today or tomorrow, it's time symmetry, which is the basis of the first law of thermodynamics, the conservation of energy.
Ah, I see. So these, like, everyday actions we take for granted actually embody these profound physical principles.
Right.
So we've got this beautiful connection between conservation laws and symmetry in physics. But here's the real head scratcher, right?
What's that?
Could we apply Noether's theorem to information itself?
That is the million-dollar question. And that's where this chapter really starts to kind of push the boundaries. Intuitively, it feels like it should fit. Information is all about the balance between, difference and similarity.
Right.
Which sounds a lot like symmetry.
It does.
But how do we actually apply these physics concepts to something as abstract as information? That's the challenge.
It's almost like we need someone to come along and completely revolutionize our understanding of information itself.
Yeah.
Someone to bridge that gap between the abstract world of information and the concrete laws of physics.
And that's where Rolf Landauer comes in. This brilliant physicist. He made this groundbreaking claim that information is physical. Not just some abstract concept floating around, but something that's actually embodied in physical systems.
Wow.
And therefore subject to the laws of physics.
Whoa, okay, that changes everything. So if information is physical, does that mean it has energy? Can it be created or destroyed like other forms of energy?
That is exactly what Landauer's principle addresses. It states that erasing information requires energy, which then dissipates as heat, increasing entropy. So yes, information has a real physical cost associated with it.
Hold on, erasing information increases entropy. But isn't entropy a key concept in thermodynamics too? It feels like we're coming full circle here.
We are. And to really illustrate this, let's take a little detour into this famous thought experiment called Maxwell's demon.
Ooh, I love this one.
Right. So imagine this tiny demon controlling a gate between two chambers of gas molecules.
Okay, yeah.
The demon, using its knowledge of the molecule speeds, can cleverly sort them, letting the fast ones through one way and the slow ones the other.
Right.
Seemingly decreasing entropy and violating the second law of thermodynamics.
It always felt like cheating a little bit.
Exactly. But Landauer's principle to the rescue. To make its decisions, the demon needs to record information about those molecules.
Right.
And when it has to erase that information to make room for more, that action, that increases entropy, balancing the equation and upholding the second law.
That's brilliant. So information isn't just a passive bystander in this thought experiment. It's an active player that ultimately ensures that the laws of physics are obeyed. But if erasing information has this physical consequence, what about creating information?
That's where things get even more intriguing, and that's where we'll pick up in the next part of our deep dive.
Okay, can't wait. So before we went to that last part, we were talking about Maxwell's demon and how erasing information actually increases entropy.
Yeah, it's wild.
It really highlights how information is more than just an abstract idea. Like, it actually has real physical consequences in the world.
For sure. It's a total game changer. And, it kind of leads to this pretty profound question.
Oh.
Does information obey the laws of physics? Or do the laws of physics actually stem from information itself? It's a real chicken or the egg situation.
Right. Which came first, the physical world or like the information that describes it?
Exactly.
But regardless, it seems like if we acknowledge this deep connection between information and physics, Noether's principle, that idea that every conservation law has a corresponding symmetry, it must apply to both.
Right. Absolutely. And that brings us back to the central question of our deep dive here.
Okay.
Is there a hidden conservation law governing information itself, just like the laws we see in physics?
Okay, so to find this potential conservation law, we need to find the corresponding symmetry. But where do we even begin to look for something like that in the world of information?
Well, we've talked about how information can be created and erased. But what if, instead of disappearing, information is just transformed? Like, what if, like energy, it can't truly be destroyed, only change from one form to another? That would imply some kind of conservation, wouldn't it?
That's a really interesting thought. But wouldn't that mean there's like a fundamental limit to how much information can exist?
It's possible.
Yeah.
I mean, think about it. Every time we process information, whether it's in our brains, computers, even at the quantum level, there's a transformation happening. Information's being encoded, decoded, transmitted, manipulated.
Right.
But what if there's some underlying principle governing all these transformations, making sure that the total amount of information remains constant?
So instead of talking about creating or destroying information, we should be thinking about transforming it. And that's where this hidden symmetry might lie. But how do we even begin to define or measure the symmetry for something as abstract as information? It's not like we can just look at it and see if it's symmetrical, right?
You're right. It's not a visual symmetry like we see in everyday objects. To find this hidden symmetry in information, we need to dig a little deeper. Perhaps at the very building blocks of information itself.
So we need to go deeper down the rabbit hole. I'm always up for that. But what are these building blocks you're talking about?
Well, in the world of information theory, you see, information is often viewed as being built upon these fundamental units called bits.
Okay.
They represent a choice between two possibilities, like a 0 or a 1 in binary code.
Right. Those digital bits that kind of make up our whole digital world.
Exactly.
Okay, so information is fundamentally discrete, built on these separate, distinct units. But doesn't Noether's theorem, which links those conservation laws to symmetry, usually deal with things that are continuous, like the smooth flowing movements of energy or objects in motion? How do we apply it to something that's built on these like separate digital units?
That is a great question, and it leads us to a fascinating area where the discrete and continuous worlds seem to intersect, the realm of quantum mechanics.
Quantum mechanics, where things can be both a wave and a particle. Always keeps us on our toes. But what does that have to do with information and symmetry?
Well, remember that the macroscopic world, the world of falling apples and car crashes, where those conservation laws are so evident, it's ultimately governed by the quantum world, the world of atoms and those subatomic particles.
So there has to be a way to bridge the gap, to show how a principle that applies to the smooth, continuous realm of classical physics also works in the quantized discrete world of quantum mechanics.
Right, exactly. And that bridge just might be found in this really cool quantum property called spin.
Spin.
Okay, now spin, it isn't really about particles spinning like little tops.
Okay.
It's more of an abstract idea, an intrinsic angular momentum that's quantized, meaning it can only take on certain specific discrete values.
Okay, so even though it's called spin, it's not actually about like physical rotation. It's more like a fundamental property of particles that exists in these discrete quantized states.
Yeah.
Sort of like how information is based on these separate, digital bits.
That's the idea. And this quantized nature of spin, it suggests that even at the subatomic level where things seem all choppy and discontinuous, there's a deeper underlying symmetry going on.
So are we saying that this tiny, almost abstract property of these quantum particles, spin, might offer a clue as to how Noether's theorem could apply to information, which is also based on these discrete units?
It seems that way.
But how does that translate to a potential conservation law for information?
Well, it's still early days, and we're really pushing the boundaries here.
Of course.
If spin, which exists in these separate quantized states, can still be linked to a conservation law through Noether's theorem,
right,
it suggests that the discrete nature of information doesn't necessarily disqualify it from having its own conservation principle.
It's like we're piecing together a puzzle, looking for clues in these unexpected places. We've gone from falling apples to car crashes to the spin of subatomic particles, all in pursuit of this hidden conservation law for information. It's pretty amazing when you think about it.
It is. It really is. And it highlights how interconnected these seemingly disparate fields of physics and information theory actually are. They might be speaking different languages, but they're ultimately describing the same underlying reality.
It feels like we're standing on the edge of this vast, uncharted territory, a realm where information and physics are inextricably linked. But before we get too carried away with these mind-blowing possibilities, maybe we should take a step back. Consider what all of this could mean for our understanding of the universe, as a whole.
That is a perfect segue to the final part of our deep dive. We'll explore those implications of a potential conservation law for information and what it could mean for our understanding of everything, from black holes to even consciousness itself.
Okay, so welcome back to our deep dive into all this. Conservation, symmetry, and the fascinating world of information. It's been quite a journey. From those everyday examples like hot coffee and car crashes to the mind-bending realm of quantum mechanics and that really intriguing idea of spin.
And through all of that, one question has really been front and center. Could there be this hidden conservation law governing information itself? If information really is physical, like Rolf Landauer said, then it stands to reason that it would have to be subject to those same fundamental principles as the rest of the physical universe, including the laws of conservation.
Right, and if there is a conservation law for information, then Noah's theorem says there should be a corresponding symmetry. But finding that symmetry, that underlying principle that governs information, that's the real challenge, isn't it?
Yeah, it really is. It's like looking for a needle in a cosmic haystack. But like we've been talking about, there are these clues, these hints, scattered throughout all these different fields. And one of the most promising leads, I think, lies in the concept of entropy.
Okay, entropy. So we talked about how it's like a measure of a disorder, randomness, and how it plays this key role in both thermodynamics and information theory.
Yeah.
In thermodynamics, the second law states that entropy always increases in a closed system. It's like the universe just has this natural tendency towards messiness.
Exactly. And in Shannon's information theory, entropy is what we use to quantify the amount of information contained in a message or system. The more random and unpredictable a message is, the higher its entropy and the more information it contains.
So we've got this concept, entropy, that's fundamental to both the physical world and the world of information. That seems like a pretty big clue, wouldn't you say?
Oh, absolutely. It suggests this profound connection, a potential symmetry principle, just waiting to be uncovered. We've been discussing how information can be created and erased.
Right.
But what if, instead of disappearing entirely, it's just being transformed from one form to another? What if entropy is what governs these transformations?
That's a really thought-provoking idea. So instead of thinking about information being created or destroyed, we should think about it as being transformed, with entropy being this key part of that process.
Exactly. And if that's the case, then maybe entropy itself is the key to unlocking this hidden conservation law for information. Think about it. Every time we process information, whether it's in our brains, computers, or even at that quantum level, entropy is involved. Information is being encoded, decoded, transmitted, manipulated. And each of these actions, it involves a change in entropy.
So are we saying that the total amount of entropy that's associated with information in the universe, that might actually be constant, even as that information is transformed and processed?
It's a fascinating possibility, isn't it? And it would have some really mind-blowing implications for how we understand everything, from the evolution of the universe to even like the limits of computation.
Okay, I am really intrigued by this idea. But how do we actually go from a fascinating possibility to a solid scientific theory? What kind of research would it take to really prove or disprove the existence of a conservation law for information that's based on entropy?
That's the exciting part. It opens up this whole new frontier of scientific inquiry.
Right.
We need collaboration. Physicists, mathematicians, computer scientists, even philosophers, all working together. New mathematical frameworks, new experimental techniques, maybe even new ways of thinking about information itself.
It sounds like we're at the very beginning of a very, very long and exciting journey. If we do find evidence for this conservation law for information, what would that mean for our understanding of the universe, of everything?
It would be revolutionary. I mean, it would suggest that information isn't just a property of physical systems, but a fundamental constituent of reality itself. Maybe even more fundamental than energy or matter.
Wow, that is a paradigm shift of epic proportions. It challenges our deepest assumptions about the very nature of reality. What would be some of the implications of this?
Well, for one thing, it would have huge consequences for fields like computer science and artificial intelligence. If information is truly conserved, it might actually set these fundamental limits on computation.
Yeah.
Dictating how efficiently we can process information and the ultimate capabilities of AI.
So there might be a theoretical limit to how powerful computers can actually become based on this conservation principle. And it would change our understanding of black holes too, right?
Absolutely. Right now there's this paradox surrounding black holes and information loss. Like, if information can't be destroyed, what happens to all the information that falls into a black hole? A conservation law for information could potentially resolve this paradox.
It's mind-boggling to think that something as seemingly abstract as information could hold the key to understanding some of the most profound mysteries of the universe.
And what about consciousness? Would a conservation law for information have implications for how we understand our own minds?
That's a question that a lot of researchers are really starting to explore now. If information really is conserved, it would mean that the information contained within our consciousness, it isn't just extinguished when we die. It would persist in some form, maybe even contributing to that overall information content of the universe.
Wow, that's an incredibly profound and thought-provoking idea. It suggests that information and maybe even consciousness is woven into the very fabric of reality, transcending the limitations of individual lives or even the lifespan of stars and galaxies.
It truly is a humbling and awe-inspiring perspective, isn't it? This whole deep dive, it's really challenged our assumptions about information, about symmetry, about the fundamental laws of the universe. It has been an incredible journey. We've explored these really profound connections between information and physics. We've pondered the existence of this hidden conservation principle, and we've even gotten a glimpse of the vast implications that this could have for how we understand reality. Even if we don't have any definitive answers just yet, the exploration itself has been incredibly enriching, wouldn't you say?
Absolutely.
It reminds us of the power of scientific inquiry, the beauty of interconnectedness, and the endless mysteries that are out there just waiting for us to uncover them. So thank you all for joining us on this incredible adventure. Keep exploring, keep questioning, and keep diving deep into the wonders of the universe.